All right, so you have to bear with me a tiny bit because I'm just doing it on this board as opposed to the light board, so because we're just in the lab. Also, my phone is my video camera, so and it's also my calculator, but like many people, so I had to pre-do some of the calculations, but I'm just going to go through. This is one data set, say for your 1 mil. You're going to have a second table like this for your 0.5, where you have all those weights, and then you have a third one for your 3 mil. My guess is that the 3 milliliter ones are going to be the most widely varying. The 1 mil ones will be pretty good. The 0.5 ones might vary a little bit more as well because it's a smaller volume, so it's a little easier to make bigger mistakes. And the 3 mil one is going to be a little bit trickier because it's going to be a lot about you squeezing the bowl. So, and that's good because what we want to be doing here is, you're going to see this calculation is a measure of variation. So the more variation there is, the more interesting it's going to be to look at. The less variation there is, the most boring this is. This isn't going to mean anything, and you're going to kind of see why in a second. So you take all the data points that you collected, all 10 of them, add them up, 0.98 plus 0.96 plus 0.99 plus 0.96 and so forth, and then divide by 10. You have 10 data points. You're going to get the X bar is called the mean, or also commonly referred to as the average. And in this particular case, the average is 0.0, sorry, not 0.098, it's just 0.981. So it's 0.981. That's the average, or mean, as we call it. The next thing we want to do is look at the difference. So what we want to try to figure out is something called standard deviation. And the standard deviation is the variation between your data points, right? So some of them are the same, 0.98 and 0.98, 0.97 and 0.97. But the thing is, if this is your average, 0.98 roughly, that means some of them are the same as the average, some of them are less than the average, and some of them are more than the average. What we want to calculate is how much variation is there? How much do we go above the average or below the average? That's the variation, or in this case, we call it the standard deviation, the deviation from the mean. And here's how we calculate it. It seems very complicated. This is the equation. If you haven't done a lot of math or algebra, it looks intimidating, but it isn't if we just take it step by step. So the first step is calculate the mean. The second step is simple subtraction. You're going to calculate the difference. X minus X bar. So that's essentially this number minus the mean. So we're going to forget about this third one because it's going to make it a little more complicated. So we're just going to round it to 0.98. We'll make it a little easier for us. So we get 0.98 minus 0.98, 0. This number 0.96, that's going to be a negative 0.02. This is not negative, it's positive. It's 0.1. This one's going to be less. This is more. This one's also more. That's the same. This is less. And this one's less. So, what do you see when we do this? If we subtract the mean from each data point, since some of them are bigger and some of them are smaller, some of them are negative numbers and some of them are positive numbers. If we were to take the average difference, that is essentially what we're doing, but we have to do more math to kind of do it properly. But that's essentially what we're doing. That's the idea. So it's like, why are you doing this? We'll look at the average of the differences. But if we were to do it the same way we did it over here and add these up and divide, they would mostly be canceling each other out. So the positive 0.02 would cancel the negative 0.02, and in the end, we would end up looking as if there's no variation. Be like, oh, it's perfect. There was no variation whatsoever. No difference. And there are differences. It's just that some are greater and some are less. So what we have to do is, we can't add these up. The way to get rid of the negatives is to square them. So you can see in this equation here, that's the sigma, means the sum, or just add up these numbers. So we're going to add up the numbers that are the data point minus the average, which is what we just did, the differences, squared. So we have to square all the differences, and that will get rid of the negative sign. So the square of 0 is just 0. it's just the number times itself. So 0.002 times, 0.02 times 0.02, 0.0004. And so that's all I'm doing here. It's not very complicated. It's just 0. So now this is the square of all those differences, and they're all positive. I got rid of the negative signs. So now we can sum them up. So we add them up. And so now the sum, so this whole thing here, the sum of the differences squared is 0.0025. So what's that mean? It's like, well, okay, that's like adding up all these numbers, roughly, before we divide. But in this case, instead of dividing by 10, we divide by something called the degrees of freedom. So you have to ask your statistician or math professor specifically the difference between why using degrees of freedom as opposed to the dividing by the sample size. But there's a number of statistical calculations that use something called degrees of freedom instead of the number of data points. It's always one less. So it's technically, in this equation, it's actually n minus 1. And n is, in this case, 10, so 10 minus 1 is 9. If we did this 20 times, you would divide by 19. If we did it 25 times, you would divide by 1 less. You'd be dividing by 24. It's just 1 less than your total. So in our case here, since I'm asking you to do 10 samples, you're going to divide by 9. But 9 is not part of the equation. The technical equation is n minus 1. So what we have to do is take this number here, which is this, and divide by 9. And that is going to be equal to so this number divided by 9 is 0.00027. And now you got to remember, this is in some kind of unit. So what unit is it? You were taking weights, and the weights were in grams. So we were technically measuring volume in milliliters, but we were actually weighing them out in grams. So this is really grams. The variation is in grams, but because we squared it here, the unit is grams squared. So if we were just to report this and say our variation is 0.00027 grams squared, it's hard to say, well, what does that mean? Because our average, our mean is in grams. So we want to just convert it back to the same unit. And to do that, you simply have to take a square root. So that's something you just have to do on your calculator. It's just what two numbers times one another equals 0.0027. So you just put in that number, and your number won't be 0.0027. It'll be whatever your data calculates out to. But for me, that's what it was after I did my 10. And I'm going to take that, hit the square root button, and I would get 0.016 grams. And that's, in our case, grams and milliliters we're assuming they're the same, because 1 milliliter, 1 gram. And so this is, for me, the variation. So I'm saying my average, the amount I pipette each time, is 0.98 when I think I'm doing 1. So I'm off a little, not too great. But every time I do it, am I fairly consistent? Like I'm always getting very close to that? Or am I wild and like really all over the place? That's what this number tells me. If it's a small number, it means you're pretty consistent, which means you're fairly precise, you're repeatable. If this is a big number, it means you need a lot more practice. You're kind of wild and all over the place, and that means in future experiments, like say when you do your serial dilutions and you turn those in, they may not look very different because your volumes weren't the same from one tube to the next tube to the next tube. Some had a lot more, some had a lot less, and early on when there's high concentrations, errors there are going to be compounded and lead to much more inaccurate results later on. So practice this. You're going to do this calculation and turn in to me the data table from all that and with your calculations, the mean and standard deviation. You're going to do this for the 1 mil volume, the 0.5 mil volume, and a 3 milliliter volume. All right, so you'll have this table and these calculations times 3 for each of those particular volumes.